Welcome to Next Gen Manufacturing Nexus. Today, we're going to pull back the curtain on something you probably never think about, but it's the invisible nervous system that runs our entire modern world. Think about it. In all these manufacturing plants, refineries, and power stations all over the globe, you've got these incredibly complex automated processes just running like clockwork. Everything's humming along, just perfectly optimized. But what happens when one tiny invisible signal goes wrong? You know, when a single sensor fails, or maybe a valve doesn't respond. All of a sudden, that whole system can just grind to a halt. We're talking millions in costs and, honestly, some really serious safety risks. So when those alarms are blaring and production has completely stopped, that's the moment an instrumentation engineer suddenly becomes the most important person on site. No question. So who are they? Well, you can think of them as the nervous system of a modern factory. They're the ones who work with the sensors, the transmitters, the valves, all the control systems. The very devices that measure and control all those crucial things like pressure, temperature, flow, you name it. Their whole job is to make sure our automated world is safe, efficient, and reliable. Okay, so what does this actually look like in the real world? Let's dive into some of the high-stakes problems these engineers are solving every single day. And believe me, these aren't just textbook examples. These are potential crises.
All right, first up, picture a massive gas pipeline. In the control room, they start seeing a pressure reading that's just consistently off. It might seem like a small glitch, right? But the effects downstream, they're huge.
And the cause? Well, it turns out to be a really crucial detail, a simple configuration error. The sensor's lower and upper range values, that's basically the minimum and maximum pressures it's set up to report, they were just wrong. This tiny data error created a massive ripple effect, causing compressors to shut down over and over again. And that means huge production losses.
Okay, let's switch gears. Now we're at a water treatment plant. And here, the sensors that are supposed to be measuring the flow of water are giving faulty readings. They're consistently showing a lower flow than what's actually happening. And the cause? You might not believe it, but it's something as simple as debris clogging up the sensors. The consequence, though, is anything but simple. The whole treatment process becomes inefficient, and that doesn't just mean higher costs. It means more pollutants are getting discharged into the environment. Not good. And, in today's super connected world, the threats aren't always physical. Let's take a pharmaceutical clean room. Here, temperature and humidity have to be perfectly controlled. But suddenly, they start seeing these random fluctuations.
This scenario, it really highlights a totally modern challenge. When they investigate, they find out the control system was hacked. Someone was able to remotely manipulate the environment. The consequence? The entire cleanroom is compromised, which puts the safety of life-saving medicines at risk. It's a huge deal.
Okay, so with problems that range from a clogged pipe all the way to a full-blown cyber attack, how on earth do they even begin to figure out what's wrong? Well, they've got this specialized toolkit that's basically designed for industrial detective work. First things first, they start with the basics. The multimeter is their go-to, kind of like a doctor checking a patient's vital signs. It tells them if the electrical signals, which are really the backbone of the control system, are healthy.
Now, for the more modern, smart instruments, they pull out something called a HART communicator. HART stands for Highway Addressable Remote Transducer, but you can just think of it as a universal translator. It lets an engineer have a direct, digital conversation with a sensor or a valve. They can ask for diagnostics, send new commands, and they can do it all without shutting the whole process down. It's pretty amazing.
And to make sure everything is absolutely precise, they use a process calibrator. This is like a tuning fork for an orchestra. It makes sure that when a sensor reads, say, 100 degrees, the actual temperature is 100 degrees. This calibration process is absolutely vital for maintaining accuracy. All right, so once they've diagnosed the problem, the engineer switches hats. They go from being a detective to being a surgeon. Now the job is to implement a really precise fix to bring the entire system back online.
And when it comes down to it, it's all about this transformation right here. They take a system that's unstable, inefficient, and frankly unsafe, and through their intervention, they restore it to a state of stability, optimal performance, and security. That's the goal.
And the fixes? They're as varied as the problems themselves. Sometimes it's a hands-on task, like literally cleaning debris out of a flow sensor. Other times, it might involve rewriting software parameters in the control system.
And, going back to our hacked clean room, it means putting in robust cybersecurity measures, like firewalls, to protect the system from any future attacks.
But, a great engineer knows that just putting out fires is only part of the job. The real goal, the bigger goal, is to build a system that's so robust that the fires never even start in the first place.
And this is why that preventative mindset is so critical. A study by the UK's Health and Safety Executive looked into major industrial incidents, and they found a truly startling statistic.
Get this. Over a third of all major accidents aren't caused by some random, unpredictable equipment failure. No, they're caused by systemic issues, the way systems are operated, maintained, and modified over time. So this is a problem of human process, not just a machine breaking down.
So, to combat this, the industry uses these dedicated things called Safety Instrumented Systems, or SIS. You can think of an SIS as the last line of defense. It's an independent automated system that's designed to shut things down safely if the main control system fails. But for it to actually work, it has to be supported by these three pillars: proper operation, proactive maintenance, and really strong management. It's a whole approach to preventing disaster.
So this all builds up to our final point. What does it really take to succeed as a modern instrumentation engineer?
Well, it's this really unique fusion of skills. Of course, you absolutely need a deep technical understanding of electronics, physics, and control systems. But honestly, that's not enough. You also need outstanding communication skills to work with everyone from operators to managers. You need meticulous attention to detail to spot those tiny anomalies, and you need a relentless curiosity to just keep learning as technology changes, because it always is.
The instrumentation engineer does. They're the guardians of the process, the detectives of the unseen, and they are that vital human element that makes sure our automated world runs safely and reliably. They are the ones who keep the machines honest every single day.